Let's talk about the VSEPR theory of molecules with 4 electron clouds. In the previous example, we talked about the VSEPR theory of 3 electron clouds. And the first thing we have to do is to draw the level structure, which we discussed in previous videos. So let's start with CH4. So let's draw the level structure of CH4. In CH4, carbon has 4 valence electrons. Hydrogen has 1 valence electron times this 4. That will give me 4. 4 plus 4 will give me a total of 8 valence electrons for CH4. All right, so the central atom here should be carbon, because carbon has a lower electronegativity. Okay, so we have carbon and we have hydrogens, 4 hydrogen atoms around carbon as our central atom. All right, so the next one to do, for every bond we have 2 electrons. So we have 2 here, we have 2 here, 2 here, and 2 here. That would give me a total of 8. So remove 8 from 8, we're going to have 0. So hence, this is the level structure for CH2. Second step says count the electron clouds. Electron clouds is a regional space where you can find electron density, where you can find electrons, electron clouds, or electron group, or electron domain, whatever word you use for it. Let's count the electron clouds in red. There are electrons over here. So that's 1. Electrons over here, 2. Electrons over here, and there are electrons over here. So we have 4 electron clouds. 4 electron clouds. So the next step says predict electron cloud geometry. Now note that for 4 electron clouds, the electron cloud geometry is tetrahedral. So the electron cloud geometry for a 4 electron cloud is tetrahedral. Okay, the next step is to ignore the lone pair and name the molecule. So ignore the lone pair on the central atom, because central atom carbon does not have any lone pair. So that means the shape of this molecule is the shape of the electron cloud, which is also what? Tetrahedral. So therefore, CH4 is tetrahedral. Talking about the bond angle for electron cloud with 4 electron clouds is 109.5 is 109.5 degrees. So basically, if I'm to withdraw my CH4, it shouldn't be drawn this way because this angle is showing angle 90. The best way to draw this is by drawing it like this. We have our carbon, we have our hydrogen here, we have our hydrogen here, we have one pointing outward in the plane, and we have one behind the plane. Okay, so we have an hydrogen here, we have an hydrogen here. So the bond angle here between every electron cloud, or between electron clouds, is 109.5 degrees. Let's take a look at SiF4. Again, the first thing to do is to calculate the number of valence electrons. So here we have silicon has 4 valence electron, fluorine has 7 valence electron times 4. That will give me 28. 28 plus 4 give me a total of, should I write that? Total of 32 valence electrons. Right, so let's determine the central atom and the terminal atom. So silicon has a lower electronegativity than silicon. Si will be my central atom, and my fluorines F. These should be my terminal atoms. Let's count number of valence electrons used up. So I have 2 electrons here, I have 2 over here, I have 2 over here, I have 2 over here. That's a total of 8 valence electrons. So removing that from 32, we're going to have 24 valence electrons. We're going to have 24 valence electrons. The next thing we have to do now is to complete the octet configuration of the terminal atoms by adding valence electrons to them. This fluorine only has 2 electrons here, so I'll add 6 more to complete its octet configuration. Okay, all done. I added 6 electrons per fluorine, so 6 times 4 will give me 24 valence electrons. So if you subtract, we're going to have 0. So hence, this is the structure or the level structure for SiF. For the next step is to count the electron clouds. Let's count the electron clouds again. I have electron clouds over here. That's around the central atom. I have 1 over here, I have over here, and I have over here. So since we have 4 electron clouds, again, the electron cloud geometry of SiF4 is tetrahedral, and the bond angle is 109.5 degrees. If I'm to withdraw SiF4, it should look something like this, something like the structure for CH4. It has the same bond angle or something close to the bond angle of CH4. Actually, the bond angle is not exactly 109.5, but slightly lower than this, something around 104.5 degrees. Well, I think you get the idea. Let's see the next one. We have ammonia NH3. NH3. The first thing we have to do again is to draw the Lewis structure of NH3. Here we have 5 valence electrons. Here we have 1 valence electron times 3. That will give me 3. 3 plus 5 will give me 8 valence electrons. Okay. The central atom here is nitrogen, since hydrogen can never be a central atom. Okay. So we have 3 hydrogen atoms around the center nitrogen atom. So I've used up a total of 6 valence electrons. Subtract it from this. We have 2 valence electrons remaining. So I assign the 2 valence electrons now. Normally, you assign them to terminal atoms, but hydrogen can only have a duet structure. It cannot have an octet structure. So I cannot assign any more electrons to the hydrogen terminal atoms. Only assign them now to the central atom. So let's assign the remaining 2 electrons to the central atom in form of lone pair. So this is the Lewis structure for NH3. Next thing you have to do now is to count the electron cloud. Electron cloud is when you can find electrons. Then we do that in red again. So we have 1 here, we have 1 over here, we have 1 over here, and we have 1 over here as well, since we can find electrons in this region. Okay. So again, we have 4 electron clouds. So the electron cloud geometry of ammonia is still what? It's tetrahedral. This is the electron cloud geometry of ammonia. So the last step says you should ignore the lone pair and name the compound. So if I ignore the lone pair, I'm going to have something looking like this. Something looking like this. Where we have our hydrogens over here, and we have our nitrogen here as central. So this forms a kind of pyramid. So we call this molecule, we say it is trigonal pyramidal. We say it is trigonal pyramidal. So this is the shape of ammonia. While this over here is the electron cloud geometry of ammonia. Let's talk about the bond angle. What do you think the bond angle will be? The bond angle normally for tetrahedral geometry is 109.5. And one thing you should know is that the electron clouds formed by non-bonded electrons, that's by lone pairs, they show a greater force of repulsion, which means that this electron cloud will push these other electron clouds further away, thereby reducing the bond angle. Bond angle used to be around this, so it's going to be reduced something lesser than this, something around 107 approximately this value. I'm not really giving you the exact value, something around 107 degrees, making the angle between the electron clouds smaller. If you're looking at water as a final example, let me quickly to space. Okay, I have water, H2O again. The first step is to draw the Lewis structure. Hydrogen has 1 valence electron times 2. So you have 2 hydrogen here. And oxygen here has 6 valence electrons. Adding it up, we are going to have a total of 8 valence electrons. Okay. And the central atom here obviously is oxygen, since hydrogen can never be a central atom. So here we have hydrogen, and here we have hydrogen, our 2 hydrogen atoms. So I've used up 4 electrons. So removing 4 electrons from this, we're going to have a total of 4 valence electrons left. Normally, we assign the 4 valence electron to the terminal atom, but since hydrogen has only a direct structure, I can only give the remaining valence electrons now to the central atom. So that means central atom is going to have 2 lone pairs, that's making it 4 electrons That's also subtracting 4 from here, you have 0. So this is the very structure for water. The next step is to count the number of electron clouds. So let's count. We have 1 electron cloud here. We have 1 over here. We have 1 over here. That's for this lone pair. And we have 1 over here for this other lone pair. Okay. So now, how many electron clouds do I have? 1, 2, 3, 4, 4 electron clouds. We mean that the electron cloud geometry is still tetrahedral. As far as it's 4 electron cloud geometry is tetrahedral. Okay. But now, what's the geometry of the molecule? What do? We ignore the lone pairs. If you ignore the lone pair, what we have now is just stuff. But now, before we do that, I mentioned up here that electron clouds formed by non-bonded electrons show a greater force of repulsion, which means that these 2 electron clouds here will push this other electron cloud over here, push it further away from each other. Okay, thereby bending it, making it more bent than it is. So let me withdraw this the right way. Show something like this. Now, because the bond angle has reduced. So somebody 109.5 has reduced around 104.5 degrees. Okay, so here we have our lone pairs, our 2 lone pairs of electrons. Okay, so ignite the lone pairs now. We are going to have something that looks like this, where this is our oxygen atom, and this over here our hydrogen atoms. Okay, so it looks like a kind of V. If you turn this upside down, it's something like this kind of V. So we say this is V-shaped. This is a V-shaped geometry, or we say it is bent. So water has a bent geometry or a V-shaped geometry.